Today, I'd like to present our research about Pitot type compact waterproof airflow sensor for Seabird Biologging. In recent years, miniaturization of sensors has led to the advancement of the biology studies. Biologging is a study of observing animal ecology using sensors and data. This study reveals the mysteries of various animal ecology. Particularly, seabirds have received attention in biologging because of their flying ability. As shown in this video, seabirds use aerial current on the sea for efficient flying. This allows seabirds to fly several hundred kilometers. As an inverse problem, it is reported that an aerial current on the sea can be estimated from seabird flight trajectory for weather information. In this research, GPS and Z-logger, several sensors were attached to a seabird as a biologging method. Then, the airflow velocity was estimated from GPS data. Adding airflow sensor and applying relative airflow measurements to biologging would allow for more accurate airflow estimation. These are the main airflow sensor types available for outdoor use. Wingwing and ultrasonic types are heavy and big for wildlife attachment. On the other hand, Pitot tube can be made in light and small size. Moreover, Pitot tube is more robust than windmill and ultrasonic types. So, Pitot tube is suitable for seabird biologging. However, there is a critical problem for attaching a Pitot tube. This is a video which was recorded by a biologging camera on the seabird. Seabirds dive into sea for playing fishing. If a normal sensor is attached to seabird, sensor gets filled with seawater and damages the sensor. Depth of the bird dive is thought to be several meters. So, waterproof pressure of 0.1 megapascal pilot. There are also other specifications. In this research, the target seabird is a straight shearwater. Based on seabird data, we designed sensor to not interfere with flight, as shown in this table. The sensor specification resolution is 1 pascal, range is 130 pascal, length is 50 millimeter, mass is several grams, and waterproofing is 0.1 megapascal. So, the sensor must be compact and highly sensitive and have high waterproofness. Here, our objective is the development of high waterproof pressure airflow sensor mounted on seabirds. In previous research, we developed a Pitot tube waterproof airflow sensor. Using cantilever type differential pressure sensor element and waterproof film allowed for both waterproofing and airflow measurements. However, there is a critical issue in this sensor. As shown in this graph, it is a trade-off between waterproof and sensitivity. This is the cross-sectional view of the Pitot tube from previous research. A cantilever type differential pressure sensor element experiences slight air leakage due to deformation. A trade-off occurs because of the cantilever's leakage and air permeable nature of the waterproof film. Furthermore, This principle causes that the smaller the area of the waterproof film, and smaller the sensitivity. If the differential pressure sensor element is a membrane type, the sensitivity becomes constant. For these reasons, we propose new waterproof airflow sensor. The differential pressure sensor element was changed to the membrane type. At the inlet of the Pitot tube, micromesh filters were attached as a waterproof function. Micromesh filter allowed air to pass through, but not water. Due to the membrane type differential pressure sensor element, the sensitivity is not affected by films. This is the principle of airflow detection. When airflow is applied to the Pitot tube, sensor element measures the differential pressure between the positive dynamic pressure on the tube's inlet and negative dynamic pressure on the square housing inlets. Following Bernoulli's law, the detected differential pressure is proportional to the scale of the airflow velocity. As shown in the circuit diagram, the sensor is controlled by IEEE communication. Sensor fabrication process is simple, requiring only 2 steps. First, the sensor element mounted on the substrate and 2 housings adhere together. Next, waterproof micromesh films were adhered to the air hose. This is the actual fabricated sensor. The sensor is 32 mm long and weighs about 1.7 grams. The housings were fabricated by 3D printer. First, we checked waterproof performance of micromesh filter. We prepared a chamber filled with silica beads and attached a micromesh filter. Water pressure was applied to a chamber using impressed pressure device. When over films water pressure resistance, silica beads get wet, then the color of silica beads changes. The pressure at this moment is micromesh filter's water pressure resistance. That was 0.40 megapascal. We measured the response of fabricated Pitot tube to differential pressure. Air pressure was applied by a pressure calibrator. This graph shows the relationship between an applied differential pressure and voltage change output. As expected, the sensor response is linear to differential pressure, regardless of micromesh films. Additionally, we measured the sensor's response to airflow velocity. Airflow was applied by wind tunnel. This graph shows the relationship between an applied airflow velocity and voltage change output. Also, as expected, the sensor detects airflow with high sensitivity regardless of the micromesh film. As well as theory, the sensor's output was proportional to the square of the airflow velocity. On the other hand, the sensor's response time is uncertain because micromesh films sandwich the sensor element. Therefore, we conducted sensor response rising test. While the airflow is generated, we placed an obstacle between the sensor and wind tunnel. The graph shows the relationship between time and voltage. As soon as an obstacle was moved out of the way, the sensor's response rose rapidly. Sensor's response rose within 0.2 seconds of the sampling rate. Here, we summarize the conclusion. We proposed the waterproof airflow sensor. We used a Pitot tube structure and micromesh films. Sensor has a water pressure resistance of 0.1 megapascal. The fabricated sensor was able to measure airflow velocity. The sensor measures highly sensitive airflow velocity regardless of the micromesh films. Rise response of the sensor is within 0.2 seconds. Here we showed acknowledgement. Thank you for listening.